So yeah, we were working on these slides. Chapter 15, I'm going to do my best to stretch out the remaining topics for the next 2 lectures at least. I think we'll at least take the rest of this one to get through it all, but I have some opportunities for us to stop and try stuff ourselves. But the goal was, for this chapter in general, and then for future ones as well, we would like to be able to make predictions. Not just we've been given data and we'd like to figure out things about it, like run some tests, like is the median this, is the mean between this and this. So we know how to do that now. The goal is to take the data that we've got and then predict new ideas. Like, all right, given, where are some numbers? Given some cars that we've seen being built before, I don't know, knowing that we got miles per gallon, knowing the price of it, can we predict a brand new car? And we know that car has 30 miles per gallon. Maybe we should be able to immediately say then that its cost is going to be, I don't know, it'll be less than $30,000 or something. We want to be able to make a prediction given some data that we have not yet seen before based on stuff that we have seen though. So find a pattern in the stuff that we've got and extrapolate from that. That's the goal. All right. And so what we went into was the idea of a linear correlation. A linear correlation coefficient, that was our R. It's a little annoying to have the drums in the background from the high school, but we'll have to deal with it. All right, so we've got a correlation coefficient. That's just a number. It's called R for short for some reason. Make up your own reason why that's true. But it's a number between -1 and +1, and it's telling us how correlated these x values and these y values are that we choose are to a line. How linearly correlated they are. So if it's like a +1 value for R, that means all your data is a perfectly increasing straight line. If it's a -1 value for R, that means your data is a perfectly decreasing straight line. And then everything else in between. 0 means there is no line anywhere. We cannot think of this as a line. This one is a good example of a 0 correlation. 0 linear correlation, at least. You can see that they're close to the middle or something, but it's not linear. There's no line that we can draw that kind of predicts values that looks like anything normal here. Just it's going all over the place. But as R gets closer and closer to either 1 or -1, you see more of a line. All right, so that's where we're going. We know how to calculate this number now. It has to do with standard units. We get the variables into standard units, we multiply them, and then we take the average of those multiplied values. All right, and again, that gives us a number that represents how closely packed on a line these values are, how linearly associated, how linearly correlated they are. Okay, and so that is kind of where we left off when we did some examples. Are there any questions about that? Because that's going to be where we pick back up, of course. It's a fun idea. We have this idea of a line. How well does our data fall in a line? We can calculate that. And so what we tried last time was with the sun's heights data set. And that's where I want to try again today. I'd like us to pick back up and let's start with the serial data set and do the same thing. All right, so let me get us started there, but that's the goal. All right, so you're gonna probably want to go to our code from class for last time. Go to the chapter 15 stuff because everything that we did was there. I'm gonna make I'll make a little separating line for what we're doing here. Whee! But what I'd like you to do is let's look at the serial data set this time. Let's read that in and do and try to calculate some correlation coefficients and see what correlates with what. Let's see if we can find any good ones. All right, so I'll give you a few minutes to play around with that. But let's at least read it in, and then I'll show you the things that we're going to probably need. So serial is a new table. Oops, make sure nothing is in that. New table. Data serial.csv. So yeah, here's our serial data set, and we've got a bunch of numerical variables. You can only do correlation stuff, calculate R values, calculate correlation coefficients with numerical variables, and so you can't just use manufacturer type for things. You can use calories, protein, fat, sodium, fiber, carbohydrates, sugars, potassium, vitamins. I guess you could use shelf, but I feel like that's more of a, even though it's a number, it seems more categorical in my mind. Weight is usually 1 or 1 1/3. That's probably not very useful. Same with cups. And then we still have no idea what a rating is, but it's a number that changes. Somebody rated something somehow. And maybe we can understand the rating better if we know what correlates with it. That would be interesting. So that's something that we could try. And so yeah, let's calculate these R values. We did it the long way last time for the sun's heights data set. So like here we are putting them into standard units and then taking the product of the values and standard units, the x values and the y values that we want to find the correlation coefficient of, taking the average because that's the formula for R. And we did though make a function for it. It's called just correlation. So if we scroll up to that, dun, 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 you're going to want to read in our serial data set and then also take this function. So let me just redefine it down here just for fun so that you can see it. So get the serial data set, play around with this correlation function on a bunch of different columns, pick x values and y values, see what correlates with what, and we'll go from there. All right? That's how we would explore a data set. So what linearly correlates with what is kind of the key question here. So I'll give you a few minutes to play around. We'll see if we can find some highly correlated things. Let me know if you have any questions. But that's exciting. So yeah, I think you're probably gonna want that up. So yeah, try out correlation stuff with the serial data set. That's the goal. I'll leave the slide not up. So you probably want that function. But it's also in our code from class. You can copy it in. First thought is that surely sugars correlates with calories, right? So we can find some strongly correlated things. I'm sure that's fine. Another minute or so to play around. There are a lot of different columns, but remember that regardless of which you choose for x and y, doesn't matter. So like if you were trying to do correlation of calories and sugars, that's the same as doing correlation of sugars and calories because you're just taking a product of standard units. And that's the same either way. Yeah, that was the idea. Let me peek ahead. That'll be fun. Alternatively, before you calculate the R values, you can maybe do a scatter plot. That might tell you what you want to see. What are some good values that correlate just in picture form? Go either one first. So, yeah. Did we find any good ones that correlated well? I feel like sugars and calories. Probably a good one to try. But we can mess with that. So I called it this data set serial. Let's see, serial dot scatter. Let's do, I don't know, calories on the x-axis and sugar, is it sugars plural? Yeah, on the y-axis. That looks decently correlated. It looks like they rounded, as the nutrition facts like to do, to whole numbers of sugars, which is interesting. But I can still see, like, you can see how it's getting bigger, of course, right? More calories equal more sugars, and vice versa. That seems pretty positively correlated. Let's see how well. So you can say correlation, and what you give to this correlation function is the name of the table serial, as well as the labels, like for what the columns are called, so calories and sugars, and it will go in and get those columns out as arrays, convert them to standard units. Oh, probably we needed that standard units function too. If I want to redefine it, sorry. Though I know it's here already. Let's take that too, just in case you didn't already copy it. So we need all those things, like that one and that one. And then it should calculate it. So it looks like, yeah, that's decently correlated. It's much more than 0.56. So the max is 1. It's not a perfect straight line, but you see that it's an increasing thing. So it's positively correlated. It's great. Any questions about that? Anything else that we found? Did we find any better correlated things? Things that are closer to 1 or closer to -1? It's like that's for sure a strong one. You can prove that. Some things that are not correlated at all, like close to 0, those are also interesting ideas. So here's some ones that I found. If we're shy today, the strongest one that I found, surprisingly, is fiber and potassium. I have no idea. I guess in fiber there's a lot of potassium in it. I have no clue how that works. Or just like if it's a more fibrous one, it's like healthier for you and maybe they fortified it more. No clue, but that is a 0.9 correlation. Impressive. Serial.scatter, fiber, potassium. Amazing. So yeah, it looks like the more fiber you have, the more potassium, and vice versa. No clue why that's true. But honestly, I don't know if these are outliers up here because I can kind of see more of a curve towards the top. You see that? It looks more like whoop. So maybe it's not linearly correlated, but it's very close to a line at least, which is cool to think about. I like that. Some values that I found that were not correlated really: potassium and what was it? Sodium. Apparently, sodium and potassium, they could just both be all over the place. Depends on what the ingredients are, I guess, in the cereal. So give me the cereal table, sodium, give me the potassium. It's like 0.03, negative 0.03, so slightly negatively correlated, but not really anything useful. So if you were to graph that, it would look more like this picture, in theory, or something similar to that, or even perhaps this, where maybe there's an outlier, who knows? Something's bringing it down. So it's one of those two options, but you can confirm that by doing a scatter plot. Why does this look like 0? Is there a line or is there an outlier? And yeah, it just kind of looks like it's all over the place. One doesn't influence the other. So that's cool to think about, that you have one number that can describe that idea to us. At least in terms of what lines are, in terms of linear association. Okay, so yeah, an example of one that I found that was negatively correlated, that wasn't super strong, but kind of makes sense if you think about it. Correlation, cereal. Apparently, calories and fiber are decently correlated negatively because if you imagine there's more, like, maybe I should think about it the other way. Let's do fiber and calories. It's going to be the same number. But think about fiber on the x-axis. Like, the more fiber you have in your cereal, as humans, we cannot digest fiber. And so that means you have less calories and the same usually it's the same serving size, like a cup of cereal. So yeah, the more fiber, the fewer real calories that your body can digest. It's supposed to be better for you. It's healthier, I guess. It's not super strongly correlated, but it's negatively correlated a little bit. Okay? So yeah, those things that we can do with the correlation coefficient. It's fun. We can explore data sets, and we can either start with a scatter plot or not, and eventually get this number that describes how linearly correlated these two values that we chose are. All right, so that's a fun exploration. Are there any questions about that? Because I want you to try something for the Pokemon data set. I think I need to rearrange these slides, but what I want to do is I want us to read in the Pokemon data set and then try to do this exploration, but there's a bunch of different numbers in the Pokemon data set. There's a ton of them. We'd like to find the most strongly correlated values, but we don't have all day to like type out individual ones. And so I want to show you a trick. I want to show you something cool that you could do with loops in Python or any other programming language, and maybe I should teach that first. So I want to teach you what's called a nested loop. Have we maybe seen this in the book or in any assignments yet? Yeah.
I've seen it because I've done.
Yeah, you've taken more computer science classes, so you've got a head start. But if you've never taken a computer science class, maybe you've never seen this before. It's a cool idea where you can put a loop within a loop. It's a little disgusting once you think about it the first time, but here's some code, and it's going to print these things. Let me prove that to you, and then we'll go from there. I don't know, make it slightly pretty. These are keywords. Print is a keyword. In is a keyword. Make array is a keyword in the language. But it won't make it bold for me. Why not? There you go. I don't know. Useful. So here's that. Let me show this to you. It's weird. It's really, really weird. Boop. It goes 1 1 1 2 1 3 2 1 2 2 2 3 3 1 3 2 3 3. So first of all, I have these two arrays. This array 1 2 3. This array 1 2 3. And do you see, first of all, just like not even understanding the code, that it's giving me every possible combination of 1 2 3 and another 1 2 3. Does that make sense? It might be easier for me to do it this way, in fact. Like, maybe we can think about it this way. Let's do strings instead, honestly. That might be easier. Unfortunately, PowerPoint really wants curly quotes, so it's going to take a second. Can I copy the normal quote? Nope. What if I do this? That's disgusting. But let me show this to you. If we type it like this, this might be a better one to think about. Or let's do XYZ maybe. Of course, that ruins the quotes, but that's fine. This is going to print 1x, 1y, 1z, 2x, 2y, 2z, 3x, 3y, 3z. And I'll show that to you. Why does it think that make array is spelled wrong? Cool. Let me show you that. I think that's probably a better example. Yeah, because you got two different things. So I got two arrays as part of these two loops, 1 2 3 and XYZ. And these A values are 1, 2, and 3 somehow. And these B values are the X, Y's, and Z's somehow. And do you see that the output, it's printing different values of A's and B's each time, and they're changing. I'll show you how they change soon. But notice how you get every combination of the values 1, 2, 3 first and X, Y, Z second. You have every single option. You want 2X, it's there somewhere. You want 3Y, it's there somewhere. Every one that you could ever want to have. Do you see how useful that is, that idea? Like, I can try every combination of values from this array as well as values from this array combined. Do you see why I might want to have that? Because that can be like, the first one can be labels for numbers, and the second one can be the same labels, and then I can try every XY pair of those labels and find correlation values for them. That's the goal. That's what I'd like to do right now. So I want to teach you why this nested loop works, though. So here's the secret. I want you to think of it as one outer loop, like here's this loop right here. It's doing stuff with an A value, right? It's taken on, like every time it runs, it's called the body of the loop, right? Every time it runs the body of the loop, A gets a chance at being one of these three values, because those are the pieces of that array. And so think of it as, all right, it chooses a value for A, and then it runs everything in its body. And so it runs this entire code, whatever it happened to be. For us, it's a loop again. It runs all of that blue box to completion. So every time it chooses a value for A, the first time it's going to choose a value of 1 for A, right? Tries that one first. And then it's going to run all of this code with A set to 1. Does that make sense? Like it's going to forget about the outer loop. It's going to run that inner code, which is another loop. Oh no. But it's going to do it with a value of A set. Okay, because that's how these loops work. They take, this is a variable name, it's going to range over all these different values in this thing that's an array, usually for us. Array or a list. So, and then it's going to do all this. So B is like, all right, for every B value in make array, it's going to run this entire blue box to completion now, right? Because that's the body of the outer loop. This is the inner loop. So B gets a chance at being X, Y, and Z. And we got to finish that off before we can like be done and loop back to the start of this loop, because that's how loops work, right? This loop gets repeated, but it runs all of the code inside of it first before it goes back to repeat itself. So now we got B going to be X, Y, or Z. The very first thing it will be is X. So does that make sense to us why the very first thing we print is 1X? Because it runs this inner line now, because it's going to repeat this loop as many times as it needs to. But A has been set, B has been set. They've both been chosen to be the very first thing in the arrays. Does that make sense why the very first output line is going to be 1X? Other questions about that? Because that's going to influence the rest of this example. So that's why we see that one. And then we are not done with this loop, right? We have to run the whole blue box to completion. Just forget about this one. Just forget this existed for a second. We have to run everything, because that's what it means to run the body of a loop. This is the outer loop running. It's got to get everything finished. So 1X, then B becomes 1Y, right? Or becomes Y. It holds Y. It gets a chance at being that value too, and it runs the body with those values set. So A has been set to 1 still, and B is now Y. You see why the next thing's going to be that now? Because it's still working on that inner thing. This is just like a big line of code as far as the outer loop is concerned. That's what it's thinking about. So then B gets a chance at being Z. And then we print AB again. And A is just not changed. It's still 1X, 1Y. Now it's 1Z. But after that's completed, we've gotten to the Z, right? B has ranged over all the values in that array. Which means that this for loop now, this inner one, is completed. Like, if there are more lines, we go on down to those lines down here now. But there aren't anymore. Which means it's time to repeat that outer loop. Does that make sense to us, what it's about to do? Because then it's going to try A with a new value, with the next value, where we were doing everything. Like, we ran the inner part with A being set to 1. Now we're going to run it with A being set to 2. And so, honestly, the B only existed as part of the loop, the inner loop, when it was running. And so kind of B doesn't exist anymore once we get down to here. We jump back up here and set A to be something different. A is now 2. We'll be like, A is 2 now. All right. And then we run all of this code. Whatever's on the inside just happened to be a loop this time. That shouldn't be too scary once you see it once. We just run all that code again with A holding this value. But okay. And then we just forget about all this while it's running. It's like, all right, we have all this code to run now with A being set to 2. Do it. You see how now it's going to be, all right, B gets a chance at being X again. And we print AB. Well, that's now 2X. 2Y. 2Z. See how it's ranging through those values? It's just holding steady on the A value. It's forgetting about that. It's running everything in here with A being set to that new value. It just happened to have been a loop on the inside again. It's a little scary, I know, but do you see the pattern there, the order? Yeah, so for the very last time, it's like, all right, after it's done, like if there were a line down here, now it would run it, but there's not. And so it's going to erase B. B was just part of the loop as it was running, and now it's done, the blue box loop at least. Now we're back again to, we jump up here, like, are there more things that we could have be A? Yes, there's one more thing. Now we could have it be 3. So A gets to be 3. That's the very last time we do things, and then we run everything. Forget about this. outer line, we run all the code in the body of the loop with A being set to 3. And okay, that just involves us running all this code, which happens to be another loop. Okay, so B gets to be X, Y, and Z all over again. Starts out at X, and then we print A and then B with a space in between. That's what the comma does for the print function. So we get the 3 and then the X. And then we're still working on this inner loop as long as it needs to be run. So then B gets a chance at being Y again. We print our 3Y, and then B gets a chance at being Z again. We print our 3Z. And then, all right, B's done. So like all this loop is finished. So all this all goes away. And then also we jump up back here and Python says, is there anything new, anything else in that array that A could take on and have a chance at being? No, it's been everybody. And so that means the whole loop is finished. And the A and the B, they both go away. But that's why we see that exact order. And what I want you to take from this is that it's trying all combinations of values 1, 2, 3, and X, Y, Z together when you nest it like this. It's called, you're nesting one inside of the other. It's like you're building a nest, like a bird. Any questions about that? It's a fun little idea. It's useful to us right now. Okay, so what I'd like you to try then is let's read in the Pokemon table. I'll get us started with that at least. And let's see. Pokemon equals table.read table. Pokemon.csv. And in this Pokemon table, there's a million things for all the different types of Pokemon that existed when this data set was made. All these values are like against, they're like 0.5, 0.251. They're not very useful values. But once you get to like very different values, it seems like we would want to do a correlation test. So like attack is a number that's different across a vast range of Pokemon. Like it could be 49, it could be all the way up to 104. That's a very strong Pokemon, right? Happiness as well is probably not a very good value to use. Whatever total is maybe interesting. Defense, like attack and defense, those are the first numbers that stick out to me as being very like widely ranging, like different values. Like maybe they correlate with each other. Like more Pokemon have stronger attacks or maybe worse at defending themselves. That seems like a fair trade-off in the world, or at least as far as the game is concerned. Base HP levels at level 50, I think. Like that's how much damage you can take as a Pokemon. That's another value that ranges a lot. That's useful. Pokedex number, not useful, I wouldn't say. Though you could think about like Pokemon released later have higher numbers. Maybe that means they have different... I don't think that's correlated with much, though. Special attack and special defense, like, that would just mean, like, if you're an electric-type Pokemon, how strong is your electric attack versus your other non-electric attacks? Your speed, stuff like that. Your weight in kilograms, like how heavy is this Pokemon supposed to be in real life, I guess, on average. Those are some values that I think are interesting. So those are some things. Maybe weight seems useful. But the question now is, we want to know like which of these values that like seem like they might be correlated are most strongly correlated. I want to try all these different options, and I think a nested loop is a great idea to use here. All right, so I think that's what I want to have you try. So here, let me show you how to get these ideas. I think what you should try doing. Oops. I'd like to see if you can do is, with this idea in mind, make an array of labels that you care about. You can get all the labels for a table by saying, I think it's just dot labels, right? Yeah. But that's probably not very useful because it's so many. There's just so many in this table. Pokemon dot labels. Yeah, it's dot labels. Gives you a big, long, almost an array of all these values, but that's too many. Most of these are like not even numerical, but these are their names, right? I feel like it's probably just better to go across and like write down the ones you care about. But try to maybe, I think this is my idea for us, try to make an array of label names, like have A be label names for the x-axis, have B be label names for the y-axis, and have, then once you're on the inner bit, you could run, instead of printing, or you want to print still, but like print a correlation value. Does that make sense? Where you've chosen an X value and Y value from labels of your table. Does that make sense? I think that's what I want you to try, and I'll show you how in a second. I'll give you a head start, though. I want to see if you can figure out how you might do that. You're still going to want to keep the print because it's not just one answer anymore. It's trying a bunch of values, and you want to print all the options still. Like you want to print the result of the correlation function. Okay, something like that. So let me have you try that. I'll give you like a 3-minute head start, and then I'll give you the hint, and then I'll have you keep on trying. Let's see if you can do that. Because that would be a very efficient thing that we could do, right? Try a bunch of labels. You're going to want to use the same array twice because it's still labels and other labels. Pick an x-axis, pick a y-axis. There's going to be some overlap. It's going to duplicate things. There's a way to get rid of that. It's a cool idea. We'll try all the combinations of these numerical labels and then go and get the correlation values for each of them. Like it'll eventually try attack versus speed. It'll also try speed versus attack. So there's a little bit of some overlap there. That was my timer. Do we see the light? Do we see the idea that could give us this? So here, let me spell it out for us. I would like to make an array of all the labels I'd like to try against each other. So like attack for sure, speed, special attack, special defense, like all those names. Weight underscore kg, perhaps. Let's try them all. All the ones that seem like that are numerical and seem interesting. Here are all the labels I care about, like attack, I can spell attack properly, defense, HP, special attack, which was like that, special defense, and speed, as well as weight underscore kg. Those seem interesting to me. Like maybe heavier Pokemon have stronger attacks. That would make sense, potentially. So with that in mind, do like a loop like this for, I don't know, X in labels. And then again, you're going to indent and say like for Y in labels. Like choose an X value, then also choose a Y value from the same array. Does that make sense? And then I can print X comma Y, which is not quite what I wanted. But you see how that's going to range over all the different combinations of these labels, like attack, 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 defense, attack, HP. It's like going to give you all the options. Some of them are useless to us, like attack, attack. That's going to be, of course, correlated 1.0 because they're the same value twice. But that's okay. Let it happen. There's ways to get rid of these, but it's going to try all the different values. It's going to try all the different combinations. It's going to have x and y, once you get in the innermost bit, range over all of those different options. And so now's the time to ask for the correlation value rather than just printing out these things. Does that make sense? We'll try that, and we'll go from there. Give you another minute to see if you can finish it, and then I'll finish it too. You still don't want to keep the prints. What are you printing? You want to print correlation values. All right, here's my thought. You can keep the x and y being printed, but in addition, print the correlation value over the table Pokemon for that label versus that label, which we've chosen for x and y. Does that make sense? Yeah. So obviously when you have the same thing twice, they perfectly are correlated with one another because this is just the same values twice. But all these other ones are interesting. It looks like the weight values are sometimes not available. So maybe, actually some Pokemon are just like ethereal mists, I think. And so maybe they don't have a real weight that you can measure. So maybe that's a bad label, I don't know. But something we can think about maybe. Maybe I should get rid of that one then. But there's ways to handle it. I don't know. It's probably easier to not deal with it. Are all these values normal now? Yeah, let's forget about the weight then. Sorry. But maybe homework would be try it with the weight. Try to like get rid of the ones that don't have any weight at all. And yeah, let's take all these values and try to, I don't know, maybe put it in a table so that we can sort and see like what's interesting. I think that would be useful. Yeah, let's try it. A lot of values are duplicated, like speed special attack is 0.44-ish, and that also implies that special attack speed is here too, same value. So here is something cool that you can do. I'm not going to test you on this idea, but there's a cool feature of tables that I don't even think is in this. When you make a new table, you can give some options. There's some like hidden arguments there that you could give names to, and there's also called, it's append. There's a numpy.append that like adds things to an array, but there's also a table.append. I just want to show that to you because it's useful for what I want to do here, to put all these values one at a time as we're calculating them into a table. So here's something you can do with tables. Like you can make a blank table, of course, like that. But you can say, give me a blank table, but also give it some labels. You can say like, I don't know, the first one is hi, the second one is mom, whatever. So there's a table with some like, it's ready for two things, essentially. Does that make sense? It has labeled names. I've just not given it any actual values under those labels. So it's kind of cool that you could do that. And then once you have that table, you can be like dot append. You can append to it, and it gives new values. You append two things now, right? You give it a list of all the values, like 1 and 2, I don't know. Something for the hi part and something for the mom part. And you can do that a bunch of times. So yeah, one at a time you append to the table, and that actually modifies the table. So append modifies the table itself. And so instead of this loop that prints, let's do something similar. let's be like, all right, so let's make a correlations table. Start it as a table with some labels that are a list of all these values I care about. I'll call it like, I don't know, X, Y, and then correlation between X and Y, values that we've chosen. Something like that. And instead of printing now, I want to append. Correlations dot append all these values, and for a weird reason, you got to give them as like something that you could go through, some either a list with these square brackets or an array. I'm not going to test you on this fact, but it's just kind of cool to think about. These are the values I want to add to the next row. Like add a new row with these 3 values under this ordering of labels. And so by the time it's done, I will have legitimately a correlations table with all those values that I can mess with in table form. Isn't that nice? Instead of printing it. So I hope that makes at least a little bit of sense. It's just something cool that you can do with tables. We like this. And then you better believe you're going to want to sort this, right? Dot sort by correlation value. And then to see the whole thing, because there's more than just 10, right? There's more than just 10 rows of output. You can show the entire table with a dot show. You can give numbers in there, but if you just say dot show with nothing, it just gives you the whole, prints out the whole table for you in a nice way after we've sorted it. Cool. It looks like we don't have anything negatively correlated among these values, which is interesting in itself. Nothing like when one goes up, the other does not go down. That's not a thing. It looks like defense and speed are pretty much not correlated at all. It doesn't matter like if you're a fast Pokemon that you're really good at taking attacks. Apparently. You're just all over the place. And so probably a scatter plot would be cool looking. It wouldn't show anything real there. And then we go all the way down. You see very highly correlated things. It looks like all these ones that are 1, that's just when it was the same. It's just like took on the same value twice. Those are useless to us. So it's like from here up, we kind of care about. So it looks like attack and defense, they're correlated together. Like it's just a strong Pokemon in general. It sounds like if you're better on attack, then you also are, bless you, then you're good on defense. Good to think about. So there's not really any trade-offs there. And then same for this one. You're going to see it again because of the way that we generated these values. But defense and attack, of course, those are also correlated with the same exact number. The X and the Y did not matter. So you're going to see the same values twice. Looks like special attack and special defense are just as a little bit more correlated, I guess. So that's good to know. And it looks like, interestingly, special attack and attack are not very correlated, but like defense and special defense, whatever that means. Like if you're a water Pokemon, you're defending against water types or something, other water types. But like that's very strongly correlated, and that would make me want to go to the Wikipedia page and figure out what that even means. So that's cool to think about, I think. And then this was just a quick way to get all these values at once with this nested loop. Does this make sense, this nested loop here? And what we did to achieve these numbers. Because that was just like, we're trying all these options very quickly, all at once. We don't have to type it ourselves. We let Python do the work for us. That's a cool idea. And I have something in my eyelash. But yeah, any questions about that? It's so cool. All right. If we are happy with that, that's the end of my little let's try stuff for now, at least. Yeah, I just want to show you some things, some cool ideas. Just one caveat before we move on to something interesting, like the main topic of this lecture, of this chapter at least. I want to show you that even if you have like a really good R values, like close to 1, it might not mean that things are correlated in the way that you think they are. So I'm going to show you some examples of SAT scores. Did we take the SAT in this class? Yeah. I don't think you have to take the SAT to come to community college, right? No.
Well, it's not required in California anymore.
Nice. Yeah, I was forced to take it.
California college are not required to
Yeah, I remember reading about it. That happened during COVID, right? Yeah.
After COVID ended, they're like, yeah, just stop.
Then nobody cares. That's kind of nice. One less way. Okay. Does it help you or does it?
That doesn't matter.
Doesn't matter. Cool. So yeah, I was forced to take that. I'm glad you guys don't have to if you don't want to. But here are some scores from different states where the students took the SAT back in apparently 2014. when everyone was still kind of required to in most states. It's either the SAT or the ACT, right? But California was an SAT state back in the day. So let's call this SAT 2014, and it looks like this. Got a bunch of values, and you see, like, for each state, how many eligible students, I guess, took the SAT. So this North Dakota was probably an ACT state. And then this is the average scores for the different parts of the SAT test. And then the combined is like the average amounts combined. So let's sort by, let's see, let's just sort by state, I guess. Let the states be in alphabetical order. That would make sense to me. So here's this, Alabama, Alaska. It looks like Alaska was an SAT. There's California. 60.3% of students took the SAT that could have taken it, and the average combined score was 1504 among all the students who took it. So, okay. Dun, dun, dun. So, first fact. The data that we see here consist of average scores in each state for students taking the test. Like, aggregated over everybody who took the test, here is the average combined score of the California students in 2014. All right. So that's what the data is. We can do a scatter plot of this, SAT 2014.scatter. Let's do, oh no, it's usually like, I wasn't very good at the writing. It's like critical reading and math. Those are like the two ones that people care a lot about. And writing is like the essays that you wrote. So like you want critical reading and math to be good if you can, but I'm sure you know plenty of people in your life that like they're really good at math, they're not good at writing, or they're really good at writing, but they're not good at math. That happens. But we'll notice that when we're looking at these average scores, critical reading and math are correlated. They're incredibly correlated. Weird. So if we check the correlate, this is a line for sure, right? Correlation, SAT 2014, critical reading on the x-axis, and math on the y-axis. That's almost 1.0. It's incredibly correlated. So what gives? This is where we could falsely interpret this graph and this correlation value, because it seems to say that if you are good at critical reading, if you get a high critical reading score, that means you're going to get a high math score, usually. And that's not true for students, right? It's not true for individual students, usually. You're strong at one, but not the other, a lot of the time. That's a very common thing that you've probably seen among your friends, so or yourself even. So what is going on here is the question. We have to think about what the actual data that we have is. It's averages among all the students everywhere in that state. And that's what could get us into trouble. All right, so it's average scores in each state for the students. The idea here is that like we're not predicting a student's like math score from a critical reading score. We're not correlating a student's critical reading score to a math score. We're correlating a state's critical reading score to a state's math score, an average. You see the difference there? So do be careful. It's like moral of this story. States don't take tests. Students do. So what does that mean right now? So yeah, all the students have been lumped together. And so you've taken a bunch of averages. So all we can say is that there's a correlation for, or between, I guess, between the average math/reading scores. We don't have anything that says anything at all about individual students. This says nothing about individual students. So what this graph is telling us is that if in a state you have a high average critical reading score, you will also have a high average math score. Does that make sense? And so you can probably infer things about like education funding or how important that on average that state cares about its children succeeding. I don't know, something like that. You can draw those ideas, but not like a student that does really good at critical reading is going to do good at math. This is you've averaged over them. you've taken them all at once, which is not saying anything about individual students anymore, because I was definitely better at math. We all know plenty of people, right? People who are good at one subject, but not the other. And so don't misinterpret what this graph is saying. So remember your data at the end of the day. Questions about that? Does that make sense? Because it could lead you astray, perhaps. But with that, I am ready to teach you the most important part of this chapter. Are we ready? We have to have our eyes on the prize. I tried to keep us there last time, but the goal of this entire chapter is we needed to start with the correlation coefficient. We needed to get a number. It described how well the data could be arranged on a line. Our goal is to use and create that actual line finally. Draw the line through this linear correlated data if we know that it is very well correlated along the line. Let's actually find the equation of that line and use it to predict things, right? Because if we had a bunch of values that look like this, the whole goal for us should be okay, we know that it's very well linearly correlated. Maybe the best line that we could possibly draw through the data looks like that. That gives us a way to predict things, doesn't it? It's all right, you give me an X value. I will go look on the line at that X value and say, that's a really good prediction. If I haven't seen a value before that had that value, that's a really good prediction of what the Y value should be for some new data point. Does that make sense? If you give me somebody else who had an X value here, I can go look on the line and say, all right, probably for this new data point where the X value is that, the Y value is probably that. Does that make sense? That's what we'd like to be able to do, to use this idea. If we know it's correlated, the R value was high, let's use that to create an equation for a line and use that to predict new data points, what their Y value should be for a given X. You see that? So R is not just a number. It should describe that line in some way. What does the line look like that goes through these points? The best one that could possibly go through them. All right? So, yeah, that's where we're going. We're going to use that line to predict things. We're going to actually draw the line. All right? So the closest we got to drawing the line was this at the very start of the lecture. I haven't given you the actual way yet. We did this family height stuff, right? Where we did we made a little prediction function that went and found the average parent heights between a certain value, and we averaged those together and use that to predict the height of a child. Remember all that? So let me just show that to you all over again, because what I want to do is use that to talk about this magical line, which is called the regression line. The linear regression line. Whee! Scrolling. A lot of stuff in this chapter. So that is the goal, and the very first part of it is to first understand what we're after. So yeah, we want to do something just like we did up here. Is there a good we had this one, we called it family heights. And eventually we changed it to be called just heights. So let me redo that, re-import it there. So here is our heights table. So I'm going to go back and forth for a little bit. Just get that ready. Heights looked like that. We had our predict child function. We made a new column. Let me just bring all that back in real quick. Here was predict child. So yeah, sorry, I'm going to just go back and forth really quick just to bring everything down here one more time. Predict child, we made a new, we attached the predictions to the end here. We did that one. And then we could also do a scatter plot. I think this is enough. Come on, scroll. So we made this prediction function. We were able to attach a new column to this table, and then we can do a scatter plot on that table. It's this computed, oh goodness. Yeah, this computed, it added the prediction based on this function that found the close points, took the average. So this is not quite what we're doing yet, but it's the closest thing that we have right now. And so we can do a scatter plot of all those values. And so this is kind of what we've got. We're eventually going to do this, something similar to this, where we're going to put a real, an actual line that doesn't budge between the data and use this for prediction purposes. Okay? Use this for prediction purposes. Yeah, so what? Goal. We we want to do something like this, but without a weird function that has to like look at all the data. Like, let's use the R value. Let's have that create a line for us, but with a perfectly straight line. That's where we want to go, all right? So to get there, I do need to show you one thing. The fact that you don't need to be in any sort of unit to get a line and have it look the same. So I think I showed you this once upon a time. Like, if we change these values from like inches on each axis to standard units, kind of like we did for the cars, the miles per gallon and the price and all that, if we change those to standard units, nothing should change. Like, all these predictions should not change at all. And so let me show that to you. That's the first step. Linear association doesn't depend on the units, and that's going to lead us to the function that we care about, the ideas that we care about. So let's see. I think it's easier for me to just copy and paste stuff in so you don't have to watch me do this all day long. Give me a second. This is chapter 15. So this is what I want to do. I'll just copy and paste it in so you can have it real quick. So it's not worth typing it out. It's like most of the things we have already. So what I've done in all this code is like we've got our standard units function. Should be exactly the same. Just like take some values. And it puts them into standard units. So I've taken the heights table, and I've changed the units from inches to standard units. Like, what's the distance away in terms of standard deviations from the mean? And so these are the values. You can use those to predict children. And so we can look at the standard deviation now of these values. And I might as well just copy that in as well. Dun, dun, dun. Because what we want, is to make like, I want to do this all over again, but instead of being like, let's go and look negative 0.5 inches away, 0.5 inches away, let's do the same thing in standard units land and draw the same line in the same kind of way to show you that the units didn't really matter. That's all. So here's the standard deviation for the mid-parent values. And so if I want 0.5, because I want to go 0.5 inches up, 0.5 inches below, 0.5, how many standard deviations is 0.5 inches? Standard deviation of the mid-parent value, which was like the average parent height, is 0.277-ish. So take that, and that can be my new prediction. So instead of predicting if the height values are between negative 0.5 and plus 0.5, go in that direction, this many standard units, because that's the same thing, right? That's the same thing in standard units land. Go up and below by that amount. And so if I just do that really quick, ta-da, this is like predict child standard units land. Like, this is what it means to be close by. They're within this amount, minus close and plus close. Those are standard units amounts of 0.5 inches away. Here's all the close points in standard units land. Give the average of all those, and that's our prediction. It's the same exact graph. That's all I'm trying to say. It's exactly the same graph. It looks like this. If I scroll really quickly between them, remember this picture? Picture is exactly the same. Yeah. Maybe it's stretched a little bit because of the way the standard units work. It's putting all these on a more even playing field, but it's still a line. It's still the same linear relationship. Okay. So the units did not matter, and that's helpful for us because our R calculation was in terms of standard units, right? Our R calculation was in terms of standard units. If that does not ruin anything, we can kind of use R to make a line happen. That's the goal here, all right? So that leads us to this slide with a lot of words on it. I don't know if I care about you memorizing this too much, but you probably are going to want to write this down on your cheat sheet or something when you're taking the final. So this is the final, this is the most important thing probably of this chapter, this slide. This is like, we want to use these lines to predict values. The R correlation value, the correlation coefficient value, gives us a number that tells us how well the correlation is between the values, and it also essentially gives us a slope of that line. It gives us the best slope of the line going through the values. So linear regression, it uses a line to predict values, where you've got a bunch of values and you saw that they were correlated. You've got your R value already. Boop. You saw that they were correlated. The R value was almost 1 or something, I don't know, or close enough for what you care about. That will let us create an actual line now between those values. What is the best line that lets us predict new things? You give me a new X value, I'll tell you that the Y value that one will probably go to is that. That's what it means. That's what we want to do. That's called linear regression. Okay? That's called linear regression. It uses that line to predict values. Draw it between all the points of your data set, the best line that fits between them, and then use that to predict new things. You give me an X, I'll give you a Y. All right? That's what it does. It's wonderful. And so, yeah, the estimate of Y value is equal, this is like a function we're creating now, it actually equals R times your X value, your X input value, when both of those variables are in standard units. So R is, in fact, the slope of the line, the best possible line, when your stuff is actually in standard units land. If it wasn't, you have to convert it. That's all. All right, because then you have like an actual intercept, and then the slope is slightly different because it's like stretched or squished by the standard deviations and stuff. But that's kind of the idea. So yeah, let me show that to you. I don't know if it's worth, like, here are the formulas. Like, if you want to go back now, if this is what it's like. This is the line in standard units land. If you want to convert that back to original units, like Y in standard units is how much in normal units. You have to like cancel out the standard deviations, right? It's like subtract the average, right? Divide by the standard deviations to create the standard units amount. R times all this, the X that you're trying to predict minus its average over the standard deviation, right? That's getting it into standard units. So that's just this equation in terms of original values. And then if you solve for stuff like, all right, X estimate of Y is equal to all this stuff. It's disgusting, but I hope you kind of see the Y. It is a line. The Y equals mx plus b, because here's your X value, right? Here's the slope in normal units land. And then here, all this stuff is your intercept. Those are just constant values. Because average X and average Y, that's from your data set. It's not something that you're getting as input. You're inputting this given X that you're trying to predict. You're trying to output your estimate of what the Y should be. Okay? So, yeah, the moral of the story, hopefully, if you buy all this, there's some math that proves it, but the slope of your regression line in normal units land is this. There it is. Slope, that. And then the intercept in normal units land is, if you rearrange these, like take the average Y, there it is, subtract all this stuff, average X times whatever this is, but that's actually the slope all over again. So you can do it that way and save some time. It's like, there's the slope of your regression line. That's supposedly the best line that you could draw between all the points of your data set. And this is the intercept for that line. But there's no intercept when it's in standard units. It's just like 0, 0. It's fine. You just do it like that. All right? Because it's like it's centered around 0, 0 already when it's in standard units, because that's the average of both of them at the same time, if that makes any sense. So that's kind of why that works. You'll read about this, of course. But that is the setup. This is the equation for that best line that R kind of is secretly representing. Are there any questions about that before I show you it in code? Like that's the idea, at least. This R value really did create a line that was supposed to be the best line that's going to help us predict things now. All right? That's the goal. So yeah, I think probably it's best for me to just copy and paste those in again, because it's just, you know the formula now for the regression line. It would just take a while to copy and paste, or take a while to type these. It's everything on the slides, here they are. So this is the correlation function. We already had that one, of course. Correlation function gave us the R value, right? Give me a table, give me labels for X's and Y's. Here is how we calculate correlation. Convert to standard units first. And then the slope of the line in original units is like this, right? You get the correlation value for that table. Oops. First you get the correlation value, and then you multiply it by the standard deviation of Y over the standard deviation of X, which is all this. Give the standard deviation of the Y column divided by the standard deviation of the X column. There's your slope of in original units, of your linear regression line. And then the intercept is very similar. You can use the slope to calculate it. It's the average y for your data set. So like go and get the average of the y's, subtract from that the result of the slope function, is reuse that, that's fine. And then multiply that by the average x value of everything in your data set. That's going to be the formula. It's in terms of this original thing. Try to solve for it yourself if you can. But that's what it looks like. And that's what gives it to us. So like for our family heights, we can now use this mid-parent value, which is some number that represents like the average, or in original units, here we go, the average number of inches was, of the two parents combined, and this was the child height. We can use that these facts now to give us, oh no, is it frozen? We can use it to give us actual lines. So like here's the R value for the family heights. Family R equals correlation of the heights table, where we're trying to use mid-parent on the x to predict the child height, like for a child that we don't know, we haven't seen yet. It's family. It's the R value for the family. And this is essentially the slope then, if you think about it. It's going to be the slope of this, the best line that you could possibly draw through, which is not going to be the same as what we've calculated here. That was just a function that kind of got close in a different way. Use close values, but it will look very similar, honestly, because that was a good estimation method as well. But now we can use these functions, like give me the slope of the best line that involved that correlation coefficient. What was that? Family slope. We want to get the slope for the heights table, where we're using the mid-parent on the x-axis, mid-parent value to predict the child value. That's the family slope, and then we can do the same for intercept. Give me the intercept on the line in original units, inches, for the heights table, where we're using the mid-parent on the x and the child on the y, mid-parent to predict the child. If I want to see two values at once, I can make an array, or I could like put commas between, and this is called, let's call it family intercept. So let's output family slope, comma, family intercept. And so it looks like this is how we can predict. This is like the best line. Y equals this times x plus this to kick us off. That's our intercept. Are there any questions about that? It's like that's your line. And we can use that for prediction. We know the equation of a line now. So like you give me, I don't know, 70.48 inches. That's the average parent height. Like you've just got some new parents, they just had a child. We want to know how tall that child should be. We can calculate our linear regression estimate by doing this. We can take our slope, multiply it by the x value. So like let's say we've got a family that came in that just had a child. Their average height was 70.48 inches, because that's part of the data set. So I can show that too. And then we add to that the family intercept, because that's the line, right? This is m times x plus b, right? And so that allows us to make a prediction now. Along that best line, apparently, we're going to predict that the height of the child for the parents that have this height, on average, their mid-parent height was that, we're going to predict that the child will be this height. Does that make sense? We're reading that line off now. And there just so happen to be a few mid-parent values that are 70.48. So we can look and see, because the other way of calculating this was, let's use the similar values that are close by. So let's see how close this was, how this compares to other families that also had that height in our actual data set. This was called heights with predictions, because that was our function. We were predicting stuff. Look like this. Some of those values were 70.48. So like where the mid-parent value, where the mid-parent values are equal to 70.48. Here they all are. And we got a few of them. It looks like the child heights were all over the place, but we were predicting about this amount. That was just taking the average of things that were close by, which was honestly pretty close to the best line that the regression estimate gave us. But this is probably a better one because it considers all the data points at once, in a sense. All right, there's different reasons to want to use these different ways of predicting. This was like, look at the closest things only, or look at the whole data set as a whole. There's trade-offs there, but this was a very quick way to do a prediction. Just once and for all, generate a line. So that's very cool. I think that's what I wanted to say. So now, in addition to these, this was our predictions based on close by things, like an inch away. on either side, or half an inch away on either side, so an inch away total. Let's add to this heights with predictions table the prediction that came from linear regression now. So like attach this to all the 70.48s. Let's see how we can do that. So heights with predictions. I want to attach with a column the regression prediction, because we know how to calculate that now. That's equal to the slope for our data set, family slope, times the value in the column. So we're using midparent, right? Heights dot column midparent to do our prediction. That's our x's. Take that, y equals mx plus b, so the family intercept. Did that, and that was our table. So this was our close by, it's called the nearest neighbor prediction, and here's our regression prediction. You can see that they're pretty close, decently close. Some of them are a little bit off because this one considers the whole data set as a whole. This one only considered close by values. There are trade-offs in both places. This one took longer to calculate. You watch my computer sit and think. This one is you calculate a line, you can do some math very quickly. So there are trade-offs there in terms of speed, but let's call this something. Heights with predictions 2, I guess. I don't know. Heights with predictions 2, and then let's scatter. Let's do a scatter plot along midparent, so you can see what happened. So, all right, here are all the values in our data set, at least, of midparent height, height of child, and the yellow ones were our nearest neighbor predictions. Like for this value, 66 inches for midparent, we found all the children that were around that, or all the parents that were around that height. We took the average child height and like calculated that one. But for regression, we calculated one line that was the best one that ran through all the data points. And so it's going to look a little bit different, but it's also a perfect line as well. That's the blue stuff. And you can see that it's very close to what the nearest neighbor prediction was doing, but there are trade-offs for each of them, especially on the outsides. Like you have fewer data points around here, so like nearest neighbor might not be as good, or it might be better because you don't have as many things. So it all depends. But those are two different ways to do predictions, and now you know both. Are there any questions about what we've just done? You can calculate a number. Like the R value was secretly giving us the slope of a line. And also the intercept, if you solve for it in a cool way that had to do with standard units. So you'll be reading more about that, but I think that's really cool. Any questions about that? And yeah, I guess if we can buy all that, now I can tell you that we did this all the hard way to learn how it works. But in general, you just do it this way. In the scatter, if you ask for a scatter plot, you can actually say, give me fit line equals true. That will do all of this for us and draw the line between them. Here it is. So it will draw that new line, and that is the best estimate. That's the regression, the linear regression line. It will just draw it in for us as well. So that's kind of cool. So that includes a line of best fit for the data. Cool. And so let me show that to you. You just say, it's like the original heights table, where we haven't done anything yet. Take that and do like a scatter plot on midparent and give us a fit. And the child is the y-axis thing. And like the fit line, I want it to be true this time. There it is. It'll just do it for us. So same line that we calculated, of course. It just does it and it draws it over your graph. So now you know what that means, though. That is the best line that ran through it. In terms of linear regression, we will define that soon enough. Okay? So I think that's most of what I wanted to say. Are there any questions about any of this? So we were able to calculate a number that represents cool things. All right. Let's see. What do I want to do now? Yeah, I think we have a little bit more time. Maybe we can get started on the next thing, but we won't do it all. So I guess your question now would be, we've drawn a line between points. R was not exactly 1.0. It was not perfect. How far off are all of our estimates? Could probably be a valid question that you'd want to ask. So that has to do, the technical term for that is error. What is the error of our estimate here? Because we're using just one line and we've drawn it through it. we've calculated based on all the data at once. How good is it overall? What is how badly does it do? What's the error of it? You can ask that. All right. So let's start there, and then that's probably I'll give you a head start on that, and that's where we'll start next time. Error in estimation. So we're doing a bunch of estimates. We're using this line to calculate new values. That's the whole point of this line. We don't care about the old data anymore. We use the old data to create that line. We can use that line to make predictions about new data. Okay, that's what we want. So let's do that based on a different data set. But like, yeah, you know that the estimate wasn't perfect. It wasn't exactly -1 or +1. Or this one was like 0.5 or something. So you can always measure how imperfect your estimate was by calculating how far off, for at least the data points that you have, was the estimate compared to the actual values. Like that's called the error amount. The error equals the actual value that you saw in the data set minus your estimate for it in your estimates formula. So for us, it's the linear regression formula. Like use the line to predict how far off was it, because it's not perfect. There's going to be some differences. Okay, so yeah. Let me show that to you, and then we'll notice that we're going to need some more stuff there. Because those error values are not always going to be positive. It's like sometimes it was above the line, the real value. Sometimes it was below the line, the real value. And then if you add them all up, does it zero out? Like we don't get a good number if we add them all up, if some are positive and some are negative, right? We're going to have to deal with that. So maybe take an absolute value or something, like you know how to do. So let's get started on that, and then that will be where we come back next time. So a good table to use to think about errors. Let's do a brand new data set. We'll use this one, read table, data/baby.csv. This was the one. Oops. This was the one with the mothers who smoked and didn't smoke, and like all these different pieces of data based on the children that they had. So I'll call that the baby table. And let's just focus on, it looks like this example focuses on maternal height and then maternal pregnancy weight. So on average, if you're taller, height in inches, weight in pounds, I guess. If you're taller, you're going to weigh more during pregnancy. That's just like you have a longer body. That makes sense. So you can see that there's probably a decent correlation between these values. They've rounded all of these to like the nearest numbers. But if we do a scatter plot, maternal height and maternal pregnancy weight for all these babies, for all the mothers at least, who had these babies that we took data on, this scatter plot looks like this, which is decently correlated, right? It's like, imagine a line going that way. And you can ask for the best line due to linear regression. You can ask for fit line equals true on your scatter plots now. And so there's the line that we're using to predict the entire data set. You give me a new maternal height, say it was 60, then we're going to predict that it was like 115 pounds for that mother or something when they were pregnant. So that is a value. The correlation is not perfect, right? Because it's not a perfect straight line. So like we can ask for what's the correlation on this baby table of maternal height on the X and maternal pregnancy weight on the Y. It's not even 0.5, it's 0.44-ish. So it's not perfect. So we know what that means now, right? We know this is not a perfect 1.0 value or negative 1.0. So we'll be wrong sometimes. It does seem to be like increasing, but there's some wiggle room for different mothers, right? So it's never going to be like you give me a value, we're always going to give back the exact correct value of that mother. We're going to predict the future perfectly, but we're going to do decently well most of the time. And so what I'd like to do is maybe we can calculate the slope and the intercept, and like we can get the actual equation of this line, and then we can start calculating the error next time. Like how far off was it? So let's get those equations ready to go and see what our prediction was for each value. And that will give us a good starting point for next time, I think. So yeah, let's do that. So this is the, so remember, it's these functions that we're using up here. It's called, they work just like correlation. It's slope and intercept. And it's always going to be in the original units. So let's see here. The regression slope, so the slope of this line that the scatter plot just did for us, what is the slope of it? That's going to be, it equals the slope of the baby table with maternal height on the x and maternal pregnancy weight on the y. And the intercept is going to be all that, but call the intercept function and have it do all the nice work for us. There we go. Oh, no. That's the name of the function. And then I can show you them both by either putting a comma between them or making an array of them. Doesn't matter. So there's the slope, the m value, and here's the intercept, the b value for your equation of a line. So it looks like you give me the height of a mother. We multiply that height by this and add that. That will tell us the weight of that mother at, I guess, the final stage of pregnancy. I don't know, right before she had the baby, perhaps. So yeah, that's our equation, and we can use that to make a prediction. So like, here's our baby table. Let's attach to each row, which is a baby, I guess, another mother as well, what the estimate of our, like using their height, what the estimate of their maternal pregnancy weight was going to be. So it's not going to be perfect because we know it's never like all along the same line, but we'll see how far off we were. So we can say baby.widthColumn, our linear regression prediction, so like it's always a line, our linear prediction for this mother was, well, take the slope, regression slope, mx plus b. So here's the m multiplied by the x value. So every value in this column, what are x values? Maternal heights. So that's baby.column maternal height. Give me all those. And then add on the intercept. So plus the regression intercept. So that's going to take all the values at once. M times all the x values plus the b values. Calculate a brand new array for each row here of, one array, one value for each row of the prediction of the pregnancy weight based on the maternal height. So that we can call, I don't know, baby with predictions equals this. And let's just print it out real quick. So it looks like that. It's never perfect. It looks like for, like our prediction was a little bit off, quite a bit off for that one, better for that one. It all depends. Some of them were way off, but some of them were decently close. Like it's a line. It's trying to do a lot of work all at once. So maybe a line wasn't the best way to do it. Maybe a nearest neighbor prediction would have done better. You can try that. Now you know. But we can do a scatter plot just to see what happens. So baby.scatter, baby with predictions.scatter, using maternal height as the x. Here are our predictions. So we've calculated this line exactly now. So that's perfect. So we've got the numbers, the raw numbers, and we can see, like, because they've rounded, it's easy for us. Like, all right, for a mother whose height was 60, we know that our line only predicts one value, predicts this value, that's 116 pounds. But we know that we had a bunch of mothers all around that value. This is a decent middle point, but it's not going to be perfect for everybody. And so some of them are above, some of them are below in our original data set, and we can calculate how far off they were. All right, that's called the error. And so we can calculate it by taking the actual value, subtract from that the estimate. So like the error of, where are we? Let's do babies with predictions. The error for the first one was actual value was 100 minus our prediction was this. It was negative 21.16 pounds. Yeah. So that's the error. We can calculate the error for everybody, and then we'll see what that does. All right. So that is the goal, and I think that's where I want to stop. So we're going to see what that means. We're going to notice a cool reason to not keep them positive and negative, and that's where we're going. All right. So yeah, the moral of the story today is that R value is not a joke. It does tell you how well uncorrelated these things are, but it also gives us the line itself. We can extract equations for the line and use that to make predictions. It's very fast to do some multiplication and do some additions, right? See where on the line it was, a new value. And that's the cool bit, I guess. Yeah. So I think that's what I wanted to say for the day. Any questions about any of this before I stop the recording and let you work? All right, it's very fun. We're using our old data to predict new values.